Good morning, everyone. In this video, I'm going to discuss some examples of topology or topological spaces. Now, let me recall first that for a class to be a topology on X, the three conditions should be satisfied. First condition is that X and empty should be in the class tau. And then in the second condition, if we have here open sets or G sub alpha in the class, then the union of G sub alpha for all alpha should be in the class. Or in other words, this class here, tau, is closed under countable union. And then in the third condition, if we have here two open sets, G and H, or it is in the class, G and H are in the class, then the intersection of G and H is in the class tau, or the intersection of two open sets is open. Or in other words, this class here is closed under finite intersection. So remember these three conditions here because these are very important. We have here X and empty in the collection, and then the collection tau is closed under countable union. It is not finite. It is not only finite, but it is countable union. Here, in the third condition, this collection here is closed under finite intersection. So let's have here an example. We have this notation here, script D. This denotes the class of all subsets of X. So we have this D here, script D, is called the discrete topology. And of course, the pair here is called the discrete topological space, or simply, we have discrete space. Now, why is it called a topology on X? So, we will be showing the three conditions. Note here that this script D here contains all the subsets of X. It follows that Cx and empty are in the collection, script D. Also, the union of any number of sets belongs to the collection D, since it contains all the subsets of X. Another one, if we are going to get the intersection of any two sets in this collection, the intersection also belongs to this collection, since again, it contains all the subsets of X. So, of course, the three conditions are satisfied. Hence, this D here is a topology. Or, specifically, this is called discrete topology. As you noticed here, D is just simply the power set of X. Why? Since it is a class of all subsets of X. Now, let's have here another example. We have here script I. Actually, script I is the class with members X and empty. So we call this as indiscrete topology. And of course, the pair is called the indiscrete topological space, or simply an indiscrete space. Actually, this is a topology by observation because we only have here X and empty. So if condition number 1 is satisfied, and then for condition number 2, if we are going to take the union rather, still it is in the collection, as well as if we are going to get the intersection.
So the intersection is still in the collection. And that's why this collection here is a topology. So let's have another example. Elements 0 and 1. So if you're going to get the power set of this, we will let that as tau sub 1. So this tau sub 1 is a topology. And we denote it as this. This is the power set of x. So this is the notation. It's like it looks like 2. And then let us consider tau sub 2 here with members empty, the set 0 and x. So if we will show the three conditions here, the three conditions are satisfied. So this tau sub 2 here is a topology. Hence, the pair here is called a topological space, or specifically this is Sierpinski space. This is called Sierpinski space. So let's have another example. We will consider x be the set of real numbers. So this time, this is an infinite set. So we let x be the set of real numbers. Then we let script u here, our collection, be the set of all open subsets of R. Okay, so this collection here is the set of all open sets, subsets of the set of real numbers. So we will show if this collection here is a topology. So we will use the three conditions. Now the first condition, we have R and empty for our first condition. R, because R is our x, and empty is in the collection. So it means R and empty are open sets. It means it is in U. So in our previous discussion, we have shown that R and empty are open sets. So it means it is in the collection. Now in the second condition, the union of any number of open sets is open. So it means that the union belongs to script U. So if we have now O sub alpha in the collection, it means that if we are going to get the countable union for all alpha, it must be in the collection. Again, we have theorem there that states that the countable union of open sets is also open. So that supports our second condition to be true. Then our third condition is that if we have two open sets, say for example O sub 1, O sub 2 are open, it means it is in the collection, then we can show that O1 intersection O2 is also open. So again, we also have that result in our previous discussion that if we are going to get the intersection of two open sets, the intersection is also open. So it means it is in the class U. So the three conditions are satisfied. Therefore, we can say that this collection here is a topology. Follow? Topology. And of course, we have the pair x mu, script u is a topological space.
So that's it. By the way, let me ask some questions. What about given two topologies, tau 1 and tau 2? First question, is the intersection still a topology? It means tau 1 intersection tau 2 a topology? Another one, what about the union of two topologies? Could it still be a topology? What do you think? So, these questions can be answered in my next video.